Thank you. Let's start out with a Bobby. What good is a buffer? Thank you. Sorry, what did you say? What good is a buffer? What is it supposed to do? Maintains the pH. Yeah. Acid, add a little base, pH will stay the same. So exam question, has the word buffer in it. You're going to be using what equation? I give you all these equations, Amanda, but what equation are you going to be using? Anybody? What equation are you going to be using? pKa plus log of moles of base. Well, technically you should say moles of conjugate base over moles of conjugate acid. Right, the buffer is a mixture of a conjugate base and a conjugate acid. Add some acid, the conjugate base reacts. Add some base, the conjugate acid reacts. Okay. Pretty much buffer, everything is writing a particular reaction. Ka, Kb, Kfp, Kf. There they are. And you got to do ice. If you don't know how to write the reaction, throw away the oars in your canoe right now. You're going nowhere. Right? So, Ka reaction. How do you write it? Let's pick on next dude, Juan. How do you write a Ka reaction? Now, I want you to use the word conjugate in your answer. How do you write a Ka reaction? The conjugate acid, good, goes to... Yeah, keep going. The conjugate acid goes to conjugate base plus H plus. Give a specific example. Now, this is where your little handout I think would really help here, Eddie. Give a specific example of a Ka reaction. What could you say? What did you say? HF goes to F negative. Yeah. So he just looked in the chart in his handout until he found a Ka table, and he just wrote one. Okay. How do you write a Kb reaction and use the word conjugate in your answer, Jessica Vaughn? How do you write a Kb reaction? Conjugate base. Conjugate base. Conjugate. Oh, you're close. You forgot something, though. Plus H2O. Okay, now keep going. Jessica, you remember? Conjugate base plus OH or acid. Conjugate acid plus OH negative. Right. That's how you write a Kb reaction. Burn those in your head, Victoria. Give me a specific example, please. A Kb reaction. NH3. NH3 plus H2O. NH4, perfect. Exactly. Okay. Now you recognize where she found that NH3. She just looked and found a table that had KBs, right? Okay. But there's a whole other source in this handout of conjugate bases. Give me another one, Javier. Another KB reaction example. But you're not getting the conjugate base from that KB table. Where does he have to look? The Ka table and write its conjugate base. Do you see what I'm after? All right, so give me an example, Paulo. All right, so I want a Kb reaction, but using the conjugate base from that Ka table. Okay, so if he's looking at acetic acid, that's HC2H3O2, what's the conjugate base? There you go. Okay, Pablo, that's where you start then. C2H3O2 with a minus. Okay, keep going. Plus. After at the KB reaction. Goes to the conjugate acid. Throw an H anywhere. They like it out front. HCH. What is it? C2H3 plus OH minus. It's always the conjugate base plus water is the conjugate acid plus hydroxide. Determine the pH of a weak acid solution. Right? Well, you just have to write a K what? A reaction, and then do ice. Okay? Determine the pH of a weak base solution. Let's say it's what Pablo just said, the darn acetate. It's 0.15 molar acetate. Now, first off, write it that way. They're going to say, oh, what cation are they going to put out in front of this? Can't put an H, otherwise you don't have the conjugate base anymore. I want to do a weak base problem. Anything in group 1, exactly. Na, Li, or K, right? And you just ignore it. You recognize, oh, what's the pH of 0.15 molar potassium acetate? Oh, you ignore the group 1 metal? It's the acetate. That's got to be a base. How do you know it's a base? Because it's the conjugate base of an acid in your Ka table. Okay, so there's a whole other group of these weak bases. So you have to write the Kb reaction, just what Pablo had us write. And you do ice. But how do you get the Kb in the first place? It's not in the table. Yeah, you remember. Kw equals what? K, well, the equation, but Ka times Kb. So you got to calculate those Kb's. Okay. And I gave you that equation, but you have to calculate it. What's the difference between pH and POH? pH is negative log of H plus. POH is negative log of OH minus concentration. Remember pH equals 14? Yeah, okay. We already talked about how do you get the Kb. It's right there. Kw is Ka times Kb. Okay, now we're getting into a little more complicated stuff. How do you determine the pH at the equivalence point? So we're titrating these weak acids or weak bases, and we want to know the pH at the equivalence point. Again, all these questions are writing a Ka or a K in this, Ka or Kb reaction, then you got to do ice. You just have to figure out, oh, do I write a Ka reaction or do I write a Kb reaction? It depends on what you're forming at the equivalence point. If you're forming a conjugate base, you're going to write a Kb reaction. You form a conjugate base. If you're forming a conjugate acid, you're going to write a Ka reaction and then do ice. All right. So let's take a look at one of these. Here. Where is the titration? Oh, here's a titration. Okay. The answer is 3.55 is the pH, but let's see if we can. I'm not going to work out the whole thing. I want to set things up is what I want to do. What's the pH at the equivalence point when 22 mils of 0.2 molar hydroxylamine is titrated with 0.15 molar HCl? This is a tough question, I think, simply because you're looking at the hydroxylamine, I ain't sure what it is. But again, you either have to write a Ka or you got to write a Kb reaction. What are we forming at the equivalence point? Are we forming an acid, a conjugate acid, or a conjugate base? Yeah, there's a couple ways to remember this. If you're adding an acid, you end up with an acid. But I really don't like remembering it that way because it doesn't make logical sense to me for some reason. What I like thinking of is, why isn't it right? If this HCl is definitely a what? A strong acid or an acid. That means this must be a what? That must be the conjugate base. So we're going to have to form the conjugate acid. You're going to have to write the Ka reaction. All right. Okay. So what is hydroxylamine in the first place, Matteo? How do you find out? Yeah, look at the table. Look at the table. What is hydroxylamine? It's NH2OH. And we're supposed to be forming its conjugate acid, which is just tack on a what? NH+. Doesn't matter where you stick it. All right? Notice one thing that's going to be kind of interesting, I think. I don't know if you realize this. Whether you write this technically correct or not, it doesn't freaking matter. Do you notice this? It doesn't change the math. You just have to write it in the form of a Ka reaction. You have to write some conjugate acid goes to the conjugate base plus H+. If you write the formula wrong, you forget the plus, whatever, it doesn't change anything. You're going to get the same pH. So you'll be okay. But might as well write it correctly. You have to have the conjugate acid goes to H+ and the conjugate base. So back to where we started. Okay? But notice if you forget the plus or something, it's not going to change anything. Then we got to do ice. Okay. Now what makes this an ugly question is we don't know what the initial concentration is. Concentration is what over what? Moles over liters. But in this case, it might be more descriptive if you said moles over total liters. If you remember that, it's a big hint on where to go. All right? So my moles over total liters. Now, how do we get the moles part?
Well, you did the hydroxylamine. Because it's going to end up being the exact same thing as the
Do you hear Matteo saying? Hydroxylamine, it's the exact same thing, right? The conjugate base, the exact same thing as the conjugate acid. It forms. In other words, he's trying to say is that's the only place the conjugate acid could come from. It all gets converted from the conjugate base. One gets converted to the other. So the moles is the same. The moles of hydroxylamine is the same as the moles of its conjugate acid. So how do you get the moles of the hydroxylamine? You can set up the little equation if you like. Like as big M is moles over liters and solve for moles. Or just realize I have 0.022 liters times 0.2 moles over a liter. Either way is the same thing. You can set it, right, remember? You can set up the mole equation, molarity equation, where 0.2 would equal the moles over the liters, right? You can solve for moles. But it's the same thing. Yeah, because all of this stuff gets converted to the conjugate acid. Exactly. Now we have to find the total liters. We know part of it is going to be what volume? 0.022 liters. Now, what's the technical word for what we have to find? Equivalence point. Now, if you can remember one thing, I think will really help you with this, finding an equivalence point. They tell you the amount in the beaker. It's how much do you add from the burette, right? Everyone with me so far? That's mole bridge, because you're converting from one compound to another compound. It's a mole bridge question. So use the mole bridge. The ratio is what to what? It's always 1 to 1. These acid-base reactions, 1 to 1. So if you know the moles of one, you convert it to the moles of the other. Right? So let's see here. Where are we at? We know, what is the moles of one? What's 0.022 times 0.2? Is that 0.004? That'd be 0.0044. Is that right? I can never trust myself. It is. Okay. So that's how many moles of the stuff we really have. 0.0044 moles. But like we said, all right, 1 mole of HCl here. Now, how do I get this into volume? 0.15. You see where Pablo's looking? you have to use the concentration of the HCl to convert moles into volume. And he said put it on the bottom. He's right. Otherwise, that moles isn't going to cancel. And that's where we'll get our second liter. And that's what we'll put in right there. Okay? So we'll calculate our total volume, divide it into the moles. We'll have our initial amount. Then we just do ice. Okay? And hopefully we'll get 3.55 for the pH. Let's see. Where did we leave off here? Okay, same type of, these 6 and 7 are both the pH at the equivalence point. Okay? So just recognize what you're forming. Is it a conjugate acid or a conjugate base? If it's a conjugate acid, write a Ka reaction. If it's a conjugate base you're forming, write a Kb reaction. Destiny, what's the convention to write a KSP reaction? What was the convention? Anybody help her? What was always on the reactant side? The solid. Everybody goes to its ions. The precipitate is another word for solid. So it'd be the precipitate goes to its ion. Right? Okay, give me a specific example, Aldo. You need your table. Give me a specific of a KSP reaction. Oh, I forgot my B. PBS goes to what? Okay. And have a little solid where? Okay. Now notice there's something wrong with our reaction, but it's not going to affect your numerical answers. Right? If the charges are really wrong, it's really Pb plus 2 and S minus 2, but that's not going to affect your ice problem. All right? It's really no big deal. Okay. So there's a specific example. How do you get solubility? Nick? In ice. Find the X in ice. You write the KSP reaction, and solubility is the X in ice. When you go through all that work, Lewis, all right? You could go through all that work here, but what are the units that X is going to come out in? It's big M, which is moles over liters. Very often, they specify what's the solubility in grams per liter. Remember those questions? They hardly ever, if they don't care, just leave it alone and write big M on your X. But they specify grams per liter. How do you convert molar mass? Molar mass of what? Of the solid. Whatever the solid is, that's what you find the molar mass of. And that's how you convert to grams per liter. Okay. In these solubility questions, there's always a part A. There it is. Find the solubility of lead sulfide. Then there's a part B. And it said, find the solubility of lead sulfide in, I don't know, 0.08 molar sulfide. Okay. So you just put that 0.08 molar where? In the ice table. In which row? Yeah, in the, the I row, the S column. Yeah, sulfide column. Now, one thing that is confusing, though, is I really don't think they're that clear. Instead of writing S minus 2, they're going to write what? They're going to put what out front? And exactly. A group 1 metal. They're going to write lithium. Or they're going to write potassium. So it's going to look like 0.08 molar K2S. You just have to recognize, oh, those darn group 1 metals, you don't care about them. That's how you got the anions in solution. But how do you get the lead in solution? 0.1 molar lead plus 2. They're going to say 0.1 molar. What anion can you stick with anything? NO3. Right. That's what it's going to look like. And you ignore the nitrate. That's how they're just getting lead 2 in solution is all. KF reactions, the last type of ice problem. Mallory, what did the F stand for? Would helper stood for nobody? Formation. F is for formation. What are we supposed to be forming? What type of ions? Complex ions. Okay. So how do you write a general KF reaction? Complex ion go. The F is the hint. Is a reactant or a product? Product, so you're supposed to be forming it. So complex ion there. And then you got the metal. And the fancy word starts with an L, a ligand. Okay, give a specific example. Notice on this handout, all the tables, I don't have a KF table. So that means any KF complex ion question I give you, I'm going to give you the KF, just like the quiz. So let's just make one up. There's CuNO3, 2 with a plus. It should work. Okay. How would you write the KF reaction for that complex ion? Vanessa, how would you write it? Yeah, that whole complex ion goes where? On the product side. Okay, then what do you put on the reactant side? Cu and, well, don't worry about the charge on the Cu. Do that last. Cu plus what? Nitrate. And what charge, everybody, does nitrate have? -1. How many nitrate? 2 of them. Now you do the charge on the copper. Now, what's the charge on this side? +1. So that means both sides have to be +1. I think it's +3, right? Because you have +3 and a -2 is a +1. Right. Okay. How do you determine the concentration of a metal ion in the complex ion solution? Now, all these KFs, like here's a KF reaction, right? And the KFs are like 10 to the 19th and 10 to the 18th, 10 to the 17th. They are huge, right? So that means you're going to form all what at equilibrium? All product. There isn't any free metal floating around. It's very, very little. That's why all these questions are always interested in what's the free metal floating around. A lot of those free metals that they're interested in too could be like platinum, cadmium, and the chromium. They're really, really bad for you. But anyway, that's what can really do some damage in your body and things. But there isn't going to be very much at all floating around because these KFs are huge. So the question that we're always messing with is determine the concentration of the free metal ion solution. So, and there's 2 types of them. And again, you're doing ice on the reaction. But what type of reaction? It was a 1/KF because we want to show the complex ions falling apart. Then it's a lot easier to do ice. So we have to do a 1/KF reaction and do ice. Exactly. Okay. Now there's complex ion problems. One was, oh, hey, the concentration of that complex ion is 0.1 molar. Okay, what's the free metal concentration? You just write the 1 over Kf reaction and then do ice. And you put the 0.1 molar in the initial row under the complex ion. Yeah. Okay, so that's the straightforward way. The other way, not so straightforward. The other way was they don't tell you the initial concentration of complex ion. You have to figure it out. Okay? Now, how do you figure it out? And how do you know it's that type of question? They're going to give you a metal ion concentration, and they're going to give you a ligand concentration. You have to figure it out. So let's check out one of those. Here it is. Okay. Sufficient sodium cyanide was added to 0.015 molar silver nitrate to give a solution that was initially 0.1 molar cyanide. What is the concentration of silver ion in the solution after silver cyanide complex ion forms? And they give us a Kf. Now notice in this question, they don't give us the initial concentration of the complex ion, right? They give us the metal and the ligand. But don't let that confuse you. Go back up. The rule is the same. You know, do ice on a 1 over Kf reaction. And let it guide you what you need to do. So let's do that then. Do ice on a 1 over Kf reaction. So our complex ion has to be over here. All right. It's got to go to the ligand. And I have how many cyanides? 2 of them. Each cyanide is a negative. And they told us silver's a plus, but you can figure it out too. Okay. So in these questions, if you remember, I kind of wrote the ice table a little bit low because we have to figure out what the initial concentration is of the complex ion. So what we did is we just put in the initial amounts it told us, some converting and some realizing what's going on. Silver ion, I put what number? 0.015. That's what's there initially. Under the cyanide, I put what? Under the cyanide, 0.1. Right? That's the initial. Does that make sense? Everybody with me so far? Read it. If you look closely at it, they're always set up this way. They have a little bit and a whole lot of ligand. Because that way you can suck up all the metal, convert it all to complex ions. There'll be ligand left over, but they don't care. They want all that metal sucked up. So if all the metal gets converted to complex ion, I have 0.015 moles of it. How much complex ion am I going to get? 0.015. It's all gone now. It all got sucked up by the ligand, got converted to the complex ion. According to this, I have 0.1 moles of the cyanide. But if the silver reacted with the cyanide, I have to have more or less cyanide laying around now. I have to have less. So I got to subtract. You could just throw in 0.015. It's going to be times 2. But it would be 0.015 if there's only one cyanide for every silver. But there's 2 of them. So you have to have 0.015 times 2. So there's 2 cyanides for every silver. Okay, so might as well do the math. 0.1 minus 0.015 times 2 is 0.07. Okay. So now I'm ready to figure out, I'm ready to do my ice table. Everybody under the complex ion, I should put 0.015. Under the silver, put 0 or a dash. The cyanide, put 0.07. And then the change row, it's minus x, x. Oh, well, this guy's 2x, actually. All right. 0.015 minus x, x, 0.07 plus 2x. Okay. Now I have... This is not a Kf reaction. This is a 1 over Kf reaction. So 1 over Kf. 1 over 5.6 times 10 to the 18th. All right? That has to equal products over reactants. silver times the cyanide x times 0.0 plus 2x, and don't forget to square the guy. All over react. On an exam, I don't suggest jumping right to putting in the x's. I suggest writing the full expression, right? Concentration of silver, concentration of cyanide squared over the concentration of complex cyanide. Otherwise, you might forget to write a squared in there. Okay. Time to drop x's. Because you take 1 and divide it by 5.6 and 10 to the 18th, you get a really small number. Definitely drop x's. What can you drop? A 2x and a minus x. They got to be numbers that you're adding or and you're adding or subtracting some x's. And that x out front, you're not adding or subtracting anything to it. So this is approximately x. Don't forget it. 0.07 squared over 0.015. Then you solve for your x. So you have to figure out what 1 over 5.6 10 to the 18th is. Do the diagonal thing. Take it times 0.015. Divide it by 0.07 squared. And hopefully, you have to take 1 and divide it by that. Well, not necessarily. If this is a 1 here, you're right, but it's not. It's a 5.6. You do it on your calculator. Take 1, divide it by 5.6 and 10 to the 18th. And whatever number you get, you put in there. Okay. Hopefully it worked out for you. Let's try to, there's another one that has a twist in here. Yep. Yeah. Negative 19. Okay. How about, yes. Did you do this part? Take 1, divide it by 5.6 10 to the 18th, right? Take it times 0.015, divide it by 0.07 squared. And whatever you get is going to be your answer. Okay. Oh, what are you getting? Oh, let me just test to make sure. I might have to change it. 5.6. Probably using your calculator. Times 10 to the 18th, right? Times 0.015. Where's my 1 over x button? There it is. Take it times 0.015 divided by... Nope. You're not using your calculator correctly. Take 1, divide it by 5.6 and 10 to the 18th. How are you doing 5.6 and 10 to the 18th on your calculator? EXP, right? There's no... Everyone's doing it wrong. There's no mistakes here. You can't flip it. You have a 5.6 here. You could just flip it if you had not a 5.6, but a 1, right? There's not a 1 there. Okay. All right. Let's take a look at one that's a little more complicated here. It has a little twist. 30 has a twist. Let's do 38 first. How would you do 38? Jessica, how would you do 38? Rojas. Write a KSP reaction and do ice. Are you going to get what units will your answers be in? moles over liters. And then if it specifies, you can convert it, but it just says solubility. So whatever you get for X. Okay, does everybody agree? Write the KSP reaction and then do ice. And you're done. Is there anything to put in the initial row? How about 30? And calculate the KSP. How do we handle something like that? We already have the X. He's exactly right. Do you follow what Nick is saying? You already have the X. So in other words, still, set up the ice. It's all in terms of X, but now you just plug in what X is. Right? And is it in the right units, though? Yeah, it's even in the right units for you. So you're good to go. Initial row. Yeah. Oh. What question, for those of you who have the handout, what question would you like to work on? Or to start at the top and go down? And go down. How would you do 40? How would you set it up? Right, the Ka reaction. They're not after pH though. They're after concentrations of what's hydronium? That's H plus. There's another way of saying H plus. Technically, what H plus is in the solution, it's H3O plus. That's H plus. Just find H plus. All right, do ice. Okay, have a Ka reaction. How would you do? Well, we did those two. We did that one. How about this thing? What type of question is this?
Titration, but with 1.2 milligrams.
It's a titration question. So again, it's gonna be ice. That means it has to be ice of a Ka or a Kb reaction. And since the titration, it's going to be some work because you're going to have to figure out the initial concentration. But are you going to be writing a Ka or a Kb reaction? Now your Kb, you can use those two guides. One is if you titrate with a base, you end up with a base. Or since this is a base, this must be an acid. So you're going to turn it into its conjugate base. Right. So the conjugate base in this case is really going to be what? If you can see this, you're really on track here. There's the conjugate acid. Ignore the what? Na. So the conjugate base is going to be just the conjugate base of that thing is take away a what? H plus. All right? Really, it's this thing. All right? Because it was this. Ignore the sodium. Take away an H plus, you end up with what's the name of that? Sulfate. Right? So you have to write the Kb of sulfate. Okay. So we're about out of time. But check these questions out. All the answers, numerical answers are there. Maybe some more practice for you.